Okay, let's just dive right into this explainer, because we're exploring the fascinating, literally billions of years long journey of the universe's ultimate engines. Whenever we look up at the night sky, we aren't just looking at pretty lights. We're essentially looking at the deep history and, honestly, the main driving force of the cosmos itself, the stars. To really grasp the sheer scale of the cosmos, just consider this number. There are an estimated 300 sextillion stars in the visible universe. To put that completely wild number into a perspective we can actually wrap our heads around, that means there are more stars out there in the dark than there are grains of sand on every single beach on planet Earth combined. Insane, right? But, why does this actually matter to us down here? Well, it boils down to that famous quote, "We are all made of stardust." These aren't just distant, cold points of light. Their epic life cycles are directly responsible for creating the heavy elements that make up the rocky planets we walk on, the phones in our pockets, and quite literally, the human beings we are. So let's start at the very beginning with Section 1, Birth in Cosmic Clouds. Stars kick off their lives in these beautiful, sprawling stellar nurseries called molecular clouds, or nebulae. Inside these massive clouds, gravity acts like this relentless sculptor, just constantly crushing vast amounts of dust and hydrogen gas together. And this is not a quick process at all. It takes around 10 million years of intense incubation and building heat until a dense, glowing protostar finally emerges from the gas. Moving on to Section 2, the nuclear fusion engine. How does a star actually stay a star? It's all about hydrostatic equilibrium. Think of it like an epic, billion-year-long wrestling match. On one side, you've got the inward force, the crushing, totally inescapable weight of gravity continuously pulling all that immense mass right to the center. But on the other side, you have the outward force, the explosive energy and pressure released by nuclear fusion in the star's core. When those two forces perfectly balance out, boom, a stable, glowing star is officially born. And to truly understand the raw, terrifying power of that fusion engine, just look at the number 4 million. In our sun's core right now, temperatures and pressures are so extreme that protons are colliding violently. The result? 4 million tons of hydrogen mass are converted into pure, radiating energy every single second. Every single second. That's the engine keeping our entire solar system alive. Which brings us to Section 3, decoding the starlight. Because how do we even know all this? Well, the answer lies in spectroscopy and some truly brilliant minds. Spectrographs basically dissect starlight into a sort of barcode of colors and lines, which reveals a star's exact chemical makeup. This massive cataloging effort happened at Harvard in the late 19th century, championed by Williamina Fleming and an all-women cadre of human computers. Later on, Annie Jump Cannon brilliantly simplified the spectral classifications, and Cecilia Payne-Gaposchkin fundamentally proved that stars are overwhelmingly made of hydrogen. Annie Jump Cannon's system beautifully organized stars by their surface temperature using a mnemonic that's still famous today. Oh, be a fine girl or guy, kiss me. This scale ranges from the absolute hottest, brightest blue O stars all the way down to the coolest red M stars. And if you're wondering where we fit in, it places our very own sun squarely in the moderate yellow G class. This whole organizational concept directly led to the Hertzsprung-Russell diagram. Now, this is arguably the most important diagram in all of astronomy. It's like a true Rosetta Stone. By mapping a star's temperature against its luminosity, or brightness, it proves that a star's initial mass entirely predetermines its destiny, its lifespan, and exactly how it's going to die. Let's look at those destinies, starting with Section 4, Quiet Fates of Small Stars. When a sun-like star eventually runs out of hydrogen fuel in its core, that outward fusion pressure drops. So, gravity compresses the core, heating it up so intensely that the outer layers expand massively. It swells up into a red giant. For our sun, this phase will eventually engulf the inner planets, including Earth. Finally, the star gently sheds its outer layers into space, leaving behind a glowing planetary nebula. The bare core left behind from that whole process is called a white dwarf. And what's absolutely wild here is its density. It's an Earth-sized sphere supported only by the weird quantum physics of electron degeneracy pressure. It is so unimaginably dense that a single teaspoon of white dwarf material weighs 15 tons. Just a teaspoon. But what about the big ones? Section 5, supernovas and black holes. For massive stars, the process is far, far more extreme.
Their huge gravity forces them to squeeze their cores incredibly hard, which means they burn through their fuel furiously fast. They start fusing heavier and heavier elements, from helium to carbon to oxygen to silicon, until they finally hit iron. Now, fusing iron takes more energy than it releases. That completely breaks the hydrostatic equilibrium we talked about earlier, leading to an instantaneous, catastrophic core collapse.
So the crucial takeaway here is that this iron collapse creates a supernova. In literally a fraction of a second, the outer layers bounce off the incredibly dense core. The resulting explosion is so unimaginably intense, it can outshine entire galaxies. But more importantly for us, the immense heat and pressure of a supernova synthesize and disperse all the rare, heavy elements across space. We're talking about the gold, silver, zinc, and copper that we use every single day.
So what on Earth happens to the core that actually survives that explosion? Well, if the surviving core is between 1.4 and 3 solar masses, the collapse forces electrons and protons to merge entirely, creating a neutron star. This is a city-sized core of pure neutrons where a single teaspoon weighs 10 million tons. Sometimes they even spin rapidly, beaming radiation across space as pulsars. However, if that leftover core is bigger, if it exceeds 3 solar masses, gravity wins the ultimate victory. It crushes all that mass down into a singularity. That's a microscopic point of near-infinite density where the gravitational pull is so immense that not even light can escape. This, of course, is what we all know as a black hole.
Let's move to Section 6, the extremes of stellar mass. Just how big can these things get?
Every new discovery kind of challenges our old limits. The theoretical upper bound for a star was originally assumed to be about 150 times the mass of our Sun. But then, we found stars like R136A1 weighing in at an incredible 315 solar masses. And when it comes to sheer physical size, consider UY Scuti. It has a radius 1,700 times larger than our Sun. If you were to drop UY Scuti right at the center of our solar system, it would swallow up the Earth, Mars, Jupiter, and everything all the way out to the orbit of Saturn.
Finally, Section 7, the cosmic connection, bringing it all home.
It is a really profound realization that nature only makes these rare elements during the death of a high-mass star. The explosive deaths of high-mass stars, those massive supernovas we just talked about, are the sole reason elements heavier than iron exist absolutely anywhere in the universe. If massive stars didn't live fast and die violently, the building blocks for rocky planets and biological life simply wouldn't be here. We wouldn't be here.
Since we are quite literally made of stardust, I want to leave you with a thought to ponder. Seriously, take a look at your own hands right now. The iron in the hemoglobin of your blood, the calcium in your bones, all of it was forged in the fiery death of a massive star billions of years ago. So which long-dead exploding supernova do you have to thank for the atoms in your body? Thanks for exploring the cosmos with me in this explainer. Keep learning and keep looking up.